Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We are thrilled to have Nutty Lineal visiting us for the month. I've been trying to get him here for a substantial period of time. It's really hard to do. Michal, we should invite you, right? And then
it would be very easy.
Yeah.
The problem that I'm not sure he's joining me.
I see. Yeah, that could be. I know they're hard to control sometimes, aren't they?
But put me on your list.
Okay. Okay, so he is visiting from the Hebrew University, and he is going to tell us all about the probabilistic method and how wonderful it is. He has a spectrum in the audience from, Jung-Hong Kim, who eats, sleeps, and breathes the probabilistic method, to some people who eat other things. So, why don't you whet our appetites?
Okay, thanks, Jennifer. Okay, now you can hear me. So first of all, I must say this is a childhood dream come true. I can really paint on the walls and not being punished for that. A few ground rules. You should ask questions and make comments throughout the talk. Don't wait till the end. It's never a good idea. We have a great tradition about this in Jerusalem. I'll tell you something about this. We have a combinatorics seminar. I tried to figure out, and I'm not even sure how many years. It must have been going for about 50 years or more. And it's a great seminar where it goes for 2 hours. And it's really more like a conversation between the speaker and the audience.
Is that your teach me something seminar?
No. This I brought to you especially as a gift. But the typical thing is that somebody will come and say, well, I have only material for 30 minutes, and we tell him, don't worry, we'll not even cover that. And so once we had some famous, I will not mention names, some famous person who came to speak in the seminar. And when he finished, I think it's a very nice thing, but also fairly exhausting because of this ongoing conversation. He said, I've been lecturing all over the world, and let me tell you a few things that I found out. When you lecture in Europe, they expect you to be very dignified and come prepared and so on and so forth. When you speak in the US, they expect you to entertain them, kind of a stand-up comedians. But when you come to Jerusalem, you have to argue with the audience. Okay, but so I'm used to this. Please don't hesitate. Ask me questions, make comments. What can I do? Okay, good. So what I want to tell you is my title is The Wonders of the Probabilistic Method. And so what I want to start with is a little bit about probability per se. Just to give you some idea, my assumption is I'm not assuming anything beyond, I don't know, good high school education in math. This is, I don't want to assume anything more than that. So probability theory is a very interesting chapter in mathematics and in the history of mathematics, because that's a subject. So people were gambling, have been gambling really for centuries. And of course, they were trying to find out how to do this well and so on. And for many years, this subject had some kind of, very problematic or malafama in math. Mathematicians didn't take this seriously. And it's really just the matter of, I think, the last century that the subject has become valid, completely recognized, and also foundationally good subject. And now I think it's completely understood that this is something that every mathematician, certainly every computer scientist, must have. And so one of the main things that I'd like to do in this talk is especially to give the people who are not mathematicians some ideas about how the practice of math, how do we actually do this, hopefully perhaps dispel some myth about math along the way. So let's start with what does probability theory do? So the main things that mathematicians do, of course, is prove theorems. And there are many types of theorems. And one type is kind of theorems that are, everyone would say they're completely obvious, but they still often require a lot of work. So I will even take a step away from probability theory and mention the following theorem, the Jordan curve theory.
There's a box of.
This is supposed to be the new one, no?
Let's try another one. Yes.
That looks better? Not good? Perhaps it's the location? No, perhaps it's the angle. No, these are new. These are brand new. Usually black works the best. Finally. Okay, yeah, all over the place. So the Jordan curve theorem is really something that any human being who is being told about this would say, what? This is something that needs proof? You don't understand? Here's what it says. It says that if I draw a curve in a plane, which doesn't cut in itself, there is an inside and an outside. This is what it says, honestly. This is what the theorem says. Now, just to give you an idea, most people who graduate in math, they know about this theorem and they never see a proof of it. It's a non-trivial theorem. So that's very typical of one type of theorems in mathematics, where it should be completely obvious that the statement is true, and it's often very difficult and very sophisticated to prove it. So what do you need to, I'm not going to tell you about the Jordan curve theorem, but what it requires, so this is perhaps one myth or misunderstanding about math that I want to discuss. Somehow math, the way most people are exposed to math, it's being conceived as the most accurate part of all sciences or of all human knowledge. And to some extent this is true. What is confusing and what is not accessible to people who don't work in this area is that there is actually a very fine and interesting game, I'll try to explain this, between really doing everything very accurately and doing things in a very inaccurate way, which is still very meaningful. But there is one part in math that we always insist on, that finally when we come down to writing papers and books and so on, that's the conceptual part. At least one thing that we must know is what the definitions mean. And this is more or less the kind of thing that is necessary here. If you ask yourself, what would I do in order, you start thinking about this. How, what is a curve? What does it mean that it simply doesn't cut itself? What does it mean that there is an inside and outside? All these things, the intuition is quite clear what they are, but to mold them into accurate definitions and concepts is highly non-trivial. So being this being my canonical example of something that is obviously true but requires conceptual work, here is an analog of this, which I think is very famous, and perhaps even those of you who are not mathematicians. So this is the law of large numbers. And what this says, I'll just give it as an example that, let's say, I don't know, we take a big population, let's say the population of the US, and we want to know, let's say, their age. So we know everyone has an age if we knew all the information, and there is some average. So if you sample, it says more or less that if you sample sufficiently many samples from a distribution, distribution, and you average, the outcome is very close to the true average. So if I don't know, there are about 300 million people in the US. If I take a good sample of tens of thousands and I average their age, then I can expect to be very close to. Now, of course, in order to make this into an honest mathematical theorem, we have to understand what this means, sufficiently many. So would it be enough if from the US, I took just 10 people? Or do I have to sample 1 million? And what does this arrow mean? What is the conclusion here? And what is very close? So in order to make this into a quantitative mathematical statement, you have to work. But by and large, this is not so far from this in the sense that there is very few significant technical difficulties. Once you have really found out what the correct definitions are and how to work with them, then this is a fairly easy proof. But mind you, it took really hundreds of years until we found out how to really develop an honest mathematical theory of probabilities. It took hundreds of years, and this was a major achievement. It's an achievement, finally, when you learn this, if you're used to this type of mathematical thinking, then it's really not difficult to understand why this is a good foundation. But often these conceptual parts of mathematics take a lot of time to develop. So this is one example. On the other hand, here is a completely different example, completely different in the spirit. That this is a saying that I once heard, that it's definitely not true that science says that there are no miracles. In fact, there are miracles in mathematics, and we just call them theorems. And this theorem is such a thing. And this is called the central limit theorem. So instead of stating it in generality, which requires some more technical mathematical background, I want to just give you an example and then explain that it goes in much greater generality. So let's take one of the most standard statistical or probabilistic setups or experiments where we flip a coin many, many times. And let's say each time it comes heads, we write a +1, and each time it comes tails, we write a -1. And then we do this many times, n times, and n is large, n tends to infinity. I will return to there. That's a very important thing to discuss, but at the moment n is a very large number, and we sum these numbers. So I summed n numbers. All of them are either +1 or -1. The sum can range from +n, if all of them came out plus, to -n, if all of them came out minus. And even if you don't have any specific background in probability, you surely have the sense that it's not very likely to be all pluses and all minuses. The sum is actually going to be rather small. And this is true. So to a first approximation, I'm still not telling you what the central limit theorem is, but you can expect the outcome. We are still not there. We are still telling something simpler than the central limit theorem. You can expect the outcome to be about square root n. So now I want to tell you, among other things that I want to do along the way, is to tell you things that all mathematicians know, but they tend not to tell them to the rest of the world. Why? Because it's so obvious. We all know this, right? So, many kids in high school and so on suffer from such things. And no one ever, I think, is telling you how to think about root n. Root n is something very simple. You take a big number. Root n is the same number with half the number of digits. This is it. Cubic root, third number of digits. This is all. So now we've come to this issue of accuracy versus non-accuracy. And that's part of the game that comes around large N. We are very, very interested, again, unlike what people tend to think, we are very interested in very rough estimates, just rough understandings of what things mean. So this is the meaning of root n. What's the meaning of n squared? It's the same number with double the number of digits. Now, of course, you know, we're not talking about the fact this doesn't tell you that 17 squared is 289, which you, of course, must know. But take a number, a 3-digit number, square it, you get a 6-digit number. Which digits and so on, perhaps we care about in some context, and we will come. But if you want to understand the big picture in the mathematical language is what we call asymptotics. These are important things to understand. So roughly speaking, if n is 1,000,000, if you do this experiment 1,000,000 times, you expect to be within a window of plus minus 1,000, which is the square root of 1,000,000, around the origin. Okay, that's very good. But there is a much more accurate picture that we see here, which is really, this is fascinating. This is something that, to begin with, it looks really like a miracle. So now we can do, this is minus n. Think of an n as 1,000,000. That would be fine. And that's 0. And for every point here between 0 and n, there is some probability, there is some chance that this is where you're. So I'm sorry, I should have said something more. What the sum is, we think of it, there are at least two different ways in which you think of it. We sum the numbers. An alternative way of thinking about this, which we also is a very important subject, but I will not, we think of this as a random walk. You can either, you know, just flip the coin n times and write the numbers and add them up. Alternative, you can do it step by step. And the way you record it is you start from the origin. Heads, you move to the right. Another heads to the right. Tails to the left. And this is where your journey ends. So now you can, in other words, draw the distribution or the chance that your journey will end here. Or if this is k, what is the chance that the sum total of these pluses and minuses is exactly k? And then you get the following picture, which looks something like this. I'm sure you all, you must have seen this thing somewhere. This is the normal distribution. Also known as the bell curve. We understand this very accurately, and I'll explain to you. But here comes the, I'll come back to this in a minute. Perhaps let me say this. So if you want to understand what this is, there is a very accurate and formal way to describe it. And don't get scared. I'll just write the expression. The expression is this baby. Now, this is 2 pi. So now, it's again a story that I heard once from a probabilist who met some high school friend who took a completely different career. And he asked him, what do you do? I'm a probabilist. Tell me something. So he started telling him, and he wrote this expression. And he says, well, what is this symbol? This is pi. What's pi? Pi is the ratio between the circumference of a circle and its diameter. So, I mean, this sounds like a complete lunatic story, right? We started with coins, we flipped them heads and tails, and all of a sudden comes the cycle. What does the cycle have to, what is this number? That's, you know, Michal had a biology professor who used to call integral snakes. So what is the snake doing here? What is this number e? But these are the small miracles. The big miracle is that I described it in a very concrete fashion. This is pluses and minuses, heads and tails. But you could do here a completely different experiment. You could, for example, toss dice or anything like this. If you repeat the same thing and you sum them up or you average up, you always wind up with this curve. It's a universal phenomenon which is pretty amazing. So these are just two basic things from probability theory. We're not going to use them or anything, but just to give you an impression of what, some of the basic things that probability theory teach us. And now I want to, so this is all very fundamental. Probability theory and randomness play an extremely important role in any part of modern science. Physics tells us that in the small scale, the universe is non-deterministic. It's impossible to exaggerate. But the main thing that I want to speak about is situations in modern mathematics where probability comes in contexts where, to begin with, you have nothing. So here, okay, that's, even if you don't have any background in math, you understand that this is a matter of luck, or there is something probabilistic. You flip coins. This is somehow the most obvious picture that people have in their mind of what is probability. You flip coins, you toss dice, and so on and so forth. And now I want to start talking about areas in which you use probability in a very fundamental way, where, to begin with, there is really no reason to think that probability would have anything to do with the subject. So now I'm actually starting to talk about the probabilistic method. So I want to start with a very fundamental theorem in combinatorics and in theoretical computer science called Ramsey's theorem. So Ramsey's theorem is part of a wider class or wider area of study called Ramsey theory. And the slogan of this is that complete disorder is impossible. Now, there are already several books dedicated to this subject, and in one of them they used a motto, a statement made by Motzkin, I think in the early 50s, to illustrate the idea of this, and it says something like this. So Motzkin said, among any three people, at least two are of the same sex. Right. So you can see that this was stated. This is completely outdated. So first of all, today you say this, and even the three, I don't know. Perhaps you want to write here a bigger number to make sure. But okay. So this is. So I want to give you. Here is the perhaps most famous basic example that you often see as a riddle. And it says the following. So in a party of 6 people, there are either 3 who are mutually familiar with each other, or 3 who are strangers to each other, or both. That's also a possibility. So let me prove this to you. So even a general public talk in mathematics must have a proof, and we do this proof. So how we do this? So we denote, so every person, every participant, every guest in the party is going to be a point, or what we call a vertex. And now, for every pair, we connect them by an edge. And we use two colors. Blue means that these two people do not know each other. So let's say it's something like this. And red means that these two do know each other. They're friends or acquaintances. So first, I think I've drawn all of them, have I? This is still missing, and this is still missing. But you can see easily that this guy, and this guy, they all know each other. So this is just an example. But let us prove this theorem. It's a proof, but it's very elementary. You don't need any substantial knowledge of math. Let's prove this statement. So this is a particular thing. Of course, these blue and red could have been anything. The claim is that however I color them with blue and red, I find such a thing. Either, like here, a red triangle, or here there is no blue triangle, but either that or both. So we go to the first vertex, one of them, doesn't matter which, and I say, how many edges touch this? There are 6 vertices, so there are 5 edges. 5 edges, the majority of 5 is at least 3. So there must be either at least 3 red edges touching it, or at least 3 blue edges. So of course, the whole thing is symmetric with respect to red and blue, so let me assume that this guy has at least 3 red edges. And now I ask myself, okay, I'm sorry. These come already without thinking. So let's assume what we do is proof by contradiction. So let us assume this statement is not true, and let us look at an example which shows that this is not true. So 6 people in a party, no 3 know each other mutually, and no 3 are strangers. So let's say that this is like this. So I'm taking this guy. There are 5 edges touching him, at least 3 of the same color, let's say red. And now I ask myself, what can I say about the color of this edge? If this edge is red, then here is a red triangle, so this must be blue. What about this edge? For the same reason, this must be blue, or else this is. And also, if this edge is red, then this would be a red triangle, so this is blue. And all together, I created here a blue triangle. So what I did, how did I prove this? This is a proof by contradiction. I said, let's suppose that this is not true. Let's look at such an arrangement where this doesn't hold. And I got a contradiction. It couldn't exist. But there is something more that is interesting here. And that's, again, one of the immediate reflexes that every modern mathematician must have. When you see a statement like this, that's, generally speaking, a good method. If you fell asleep throughout the talk and you want to wake up at the end and show that you're there, you can always ask, is the bound tight? That's a good question. So we ask it, is this bound tight? In other words, would this statement be correct if instead of 6 I wrote here something smaller, let's say 5? No, so this bound is tight because I'll show you that if I wrote there 5, then the statement wouldn't be correct. So there can be a party of 5 people without any 3 knowing each other mutually, and without no 3 know each other, and no 3 are strangers. Sorry, what? So here is the example. So now we understand that this is just a matter of coloring things, and this is what we do. So now we have just 5 guests in the party, and so you see these are the blue edges. Obviously there is no blue triangle, and all the complement, all the others are red, and you see there is also no red triangle. So we can add, and the bound is tight. Meaning this is shorthand that mathematicians use to say you can't replace this 6 by something smaller. Now, this is a very fundamental theorem for us. The fact that, let me go back to this issue of complete order. Disorder is impossible.
So you proved to us that 6 is tight. How do you know that the 3 is tight?
That there is no 4. Well, you add to it any vertex and you get no 4. But yeah, that's a completely legitimate way, a different way to ask whether this is tight. And
See, he wasn't sleeping.
or at least this is what he wants to prove to us. Right. Okay. Good. Okay. So you think about it. It's really not an obvious thing at all. And there is an urban legend which actually I investigated, or I spoke to the people who investigated, which is really a nice story. That I think in the 60s, quite a well-known, so I'm told, a Hungarian sociologist called Szalai studied relationships of friendship and non-friendship among kids in school. And he found that in every class that he investigated, he found either 4 people who were mutually friends with each other, or 4 people who no 2 of which were friends with each other. So, I mean, since classes tend to be, 20, 30, these are the typical numbers, of course, what he discovered is just a special case of the statement that, so this, by the way, this theorem, when we write it in short, we write R3, 3 is 6. That's a short way. You understand what this means. 6 vertices, either you get a blue triple or a red triple. Okay. And likewise, we know that R4 is 18. So let's go over this and just make sure that we understand what this means. This means if you take 18 vertices and you color every edge between them either red or blue, you'll find what we call a monochromatic set of 4 vertices. Either you'll find 4 vertices, all edges among whom are blue, or you find 4 vertices, all edges among whom are red. And again, this is tight. This is tight means there is an example with 17 vertices where there is no blue 4-tuple and no red 4-tuple. So that we know. And perhaps now that you know this, or let me come back to Szalai for a moment, but this being Budapest, he had been in class with Vera Schoch, who was a very famous combinatorialist. And so he went to discuss, and he went to discuss with some of the greatest combinatorialists of this era, with Paul Erdős and with Vera Schoch and with Paul Turan. And they told him that, yes, you've discovered, what you've discovered is just a special case of this mathematical theorem. And I'm not even sure exactly what happened, but the obvious thing that would have happened elsewhere didn't happen. That's so you must have the right kind of friends, I suppose. But once you get into this game, you could start asking things like, what about R55 and R66? And if you are trained as a mathematician, you may perhaps ask, what about RNN? So let me tell you, we don't know. We only know that this is between 48 and 43. We don't know this number. So you would ask, I mean, how stupid can you people be? You can't tell what this number is? No, it's very difficult. And if you think about it a little bit, then certainly no straightforward attempt to do this by computer has any chance of telling us the answer. It's very plausible that eventually, if we know this number, it's quite obvious that we will be using computers in some way. But this is very difficult. And people have been, anyone who would determine this, would certainly be celebrated. And the late Paul Erdős, who, the grandfather of modern combinatorics, used to say that if aliens from Martians would land on planet Earth and say, either you tell us what R55 is or we destroy all of you, then the right thing to do is to get all the scientists, all the mathematicians, all the computers on the planet and work hard and give them the answer. But if they say the same thing with R66, then the only way to do is to find ways to destroy them. So these questions are very difficult. And what do we do? So again, if you have the naive thought about mathematics, you'd say, okay, so this is what we can. This, perhaps with the huge effort of lots of people, and beyond this, and so the game is over. But no, this is exactly one point where the asymptotic perspective really is very interesting. We don't expect to know these numbers accurately. We don't even know what they are for n equals 5 or 6. But we can still ask ourselves, and this turns out to be a very interesting problem, and there are lots of interesting and open questions here that people investigate. How does this grow with n? How does this depend on n? So now that we understand that square root is just cutting the numbers in half, this is of course going to be a very big number. So a question would be, don't tell me this, perhaps this is what I want, but okay, don't tell me what this number is. Tell me how many digits does it have. So to tell how many digits a number has, this is what it's called the logarithm. Again, something that all mathematicians know, but they don't tell you in school. Today we study the log function. What is the log? How many digits a number has. That's the truth. This is the meaning of a log. So you could ask yourself, how many digits does this number have? And we know, in fact, if you understand this, by the way, let me just say that this proof, if you followed it, how this proof went, is really, and you just have the mathematical training, you don't need anything beyond this, then you should be able to prove to yourself what I'm about to tell you.
Why do you need two numbers? It has to be symmetrical, right? 4, 3.
No. For example, here is you're right, good question. So for example, let me say, what does R34 mean? It's actually equal to 8. Let's go over this. Good question. This means if you take 8 vertices and you color everything blue or red, then you'll either have a blue set of 3 or a red set of 4. Okay, so it makes perfect sense to ask about, the two numbers don't have to be the same. But in general, we tend to try and speak about the simplest situations. Here there is really just one parameter that we speak about. So it's easier to, but these questions are very interesting. Okay? It doesn't have, the question makes perfect sense even without the symmetry. The blue triple and a red fourtuple, that's a completely legitimate and interesting question. And usually you actually develop the theory in more generality, but I just want to reduce okay, so what do we know? We know that R and N, and this is what I'm trying to tell. Essentially, the same argument, the same proof that worked here is less than or equal 4 to the n, which is the same as 2 to the 2n. So what does this mean? If you write the number in binary digits, in bits, this is a number with 2n bits. At most. At most 2n bits. This is what it says. And now we'd like to get a lower bound. So this I'm telling you, I don't do the details of this, but essentially the same argument that worked for us so well here, if you just have the mathematical training of how to write a proof, a formal proof, you should be able to take this proof and turn it into a proof of this. It doesn't require any new ideas. It requires a little bit of, the skill of writing formal mathematics. What about the lower bound? So before, this picture showed to us that R33 is strictly bigger than 5. It's not 5, because this is an example. So you would think that in order to get a lower bound, and this was by example, right? So the natural thing would be to expect that this comes by example, that somehow we will find ways to color the edges red and blue without having a large blue set and neither a large blue set nor a large red set. So the answer is, at the moment, we don't know how to do this. You would really love to be able to do this. This is a major question. But we don't know how to do this, to construct examples. And in this spot comes in the probabilistic method. So this is what I'd like to explain to you. This is somehow the crux of this, the main point in this lecture. So perhaps my parents were right about not writing on the walls. Huh? They had a point there. Okay, good. Okay, so how are we going to do this? So one of the great things about doing anything like science and art and so on is that you're allowed to think the unthinkable. What physicists usually call Gedanken experiment, or a thought experiment. We'll start by doing a thought experiment. And so let's try and let's write a huge table. So we are not going to actually write it. We are thinking about such a huge table. And the rows of these tables, so we're picking some number n. N is an integer, a large integer. Think 100. We want to understand how large can a graph be. We color it red and blue. When does it have to either contain a set of 100 vertices with all edges blue or a set of 100 vertices with all edges red? This is what we'd like to understand. These numbers are fantastically big. This is why we're unable to determine things like R55 or R66. They're really, really big. So, but we still are allowed to think about them. So this is a list of all possible ways to color the edges red and blue. So we don't know. There is a little n, there's little n and big N. Big N is how many vertices there are in the graph. Little n is this 100. We want to understand whether or not there is what we call a monochromatic set of n vertices. So here comes the list of all possible ways to, this is a fantastically large number. No one is going to actually write such a table, but we still think about it. It's very useful. And here, there is another, so this table is huge, both horizontally and vertically. Here is a list of all sets of little n vertices. So the graph has altogether big N vertices. Inside here live little n. And now this is in this array, we write here either 0 or 1. 1 here means, so let me, just that even here I'm able to write, let's just for a second say that n is 20 and n is 5, just for illustration. So this could be, for example, corresponding to 5 numbers here, let's say 3, 8, 11, 19, and 20. This is a set of 5. And now I ask myself, in this particular coloring of the edges, is this set completely red? And let's say I hold another table with blue, okay? Well, perhaps yes and perhaps no. Perhaps in this coloring it is, in this coloring it isn't. And now, what do I want to show? I would like to show, this is a lower bound. I would like to show, let's say I've selected my numbers correctly. I still don't know what they are. But I would like to show that there is a coloring with no n vertices, all edges among whom are blue, and the same with red. No monochromatic set of n vertices. How do I see this in the table? What is such a thing? I mean, again, this table doesn't really exist anywhere. I'm just thinking about this. But had I been able to work with this table, how would I see this? I would see this, if you think about it for a moment, this is a row. A row is a coloring in which everything is 0. Because a 1, for example, this coloring will not do. Why? Because in this coloring, this set is monochromatic. And what I'm looking for is a coloring in which no set of n vertices is monochromatic. So the question, again, with this completely imagined and unrealistic thing to work with table is, if I had created this table, would there be a whole row of zeros? This is exactly what I'm looking for. And we still don't have, just to remind you, we're here for a talk on probability theory. There is still no probability, but it will come in just at the punchline. Well, what can you do? How can you approach such a thing? If, that's at the moment a big if we can show that the average number of ones in each row is smaller than 1, then a row of 0 exists. Right? If, to high schoolers, I usually say, if your average grade, well, here it's in America, it's a grade, we do by a grade of 100. If let's say your average grade in all courses is 87, this means there is at least one class in which your grade was not higher than 87. And if the average, these are all, how many ones are each row? That's an integer. And if you average integers and the outcome is, let's say, 0.9, not positive, non-negative integers, and the outcome, the overall average is 0.9, then at least one of them must have been 0. So that's the approach we are going to take. Again, with this imagined table, can we perhaps show that this holds? If the average number here is less than 1, then there is 1 where the sum is 0, when there is only zeros, and this is exactly what we want. So how are we going to now connect it to probability theory? We turn this whole business into a question of probability. What do we do? Instead, so as I said many times, this is something we cannot really directly work with. But there is something else closely related with which we can work really, really well. We can take these n vertices, and for each edge, we flip a coin. If it's heads, we mark this edge by red. So we pick these two vertices, this and this, and we now flip a coin. If it came out heads, this edge goes red. And for this and this, we also flip a coin. If it comes out tails, we do it in blue. And now we can ask ourselves, really, what is this average? So how many ones do we expect to see in every row? So let me tell you what the numbers are that we have to calculate. And then it turns out that this is actually very, very simple. So what is the average number of ones in a row in this table? That's the same as the average number of monochromatic sets of n vertices. Okay, so let's calculate this. I'm not going to actually do the calculation, but I'm going to tell you what goes into this calculation. Then, again, if you are trained enough in this, you plug the numbers in. So a simple thing is 2. This is for red and blue. It could be monochromatic red, it could be monochromatic blue. Now I write here just how many columns there are here. So what is this? The number of sets of n vertices from a big set of big n vertices. And if you remember something, this is what we call a binomial coefficient. That's the name we call it, and this is something we understand very well. And now what I have to write, and this is the only place where really probability comes in. When I do this experiment here, when I flip the coins, I have to write down here, what is the chance that a given, now I'm looking at a particular position here, or a particular column. What is the chance that a particular set of n vertices is all blue? And I'll say a word about this in a minute. That's the expression if you care for such things. If it's true, if it is true that this is less than 1, then we're in exactly the situation that we were hoping to get. The average is less than 1, and therefore there is a coloring in which no set of n vertices is. So let me say a word about this number. This is how many edges are there among n vertices. And now, for each one, I have to flip the coin. It has to come out always blue. That happens with probability 1/2. And you take 1/2 to that part. And now you have to do a little bit of calculations. And you find out. So eventually, what do we know? Let me just summarize what we know in this area. So we know that Rnn is less than 4 to the n and is bigger than √2 to the n. So this number has 4 times more digits than this. And anyone who would be able to improve these bounds would be a huge hero for combinatorialists and for mathematicians in general. But this is the best that we know. But the main thing is this problem had no relationship with with probability whatsoever. And yet, this is the best thing we're able to do. So thinking about non-probabilistic things in probabilistic terms is a huge help. What is my situation with time? I could stop here and I could tell you another story of 6-7 minutes. How is this? Jennifer, what should we do?
6-7 minutes.
6-7 minutes. I'll do something quick. So yes, please. There. Yes, that's the total number of vertices, and we want to find little n sets, a set of little n vertices which is monochromatic.
Doesn't that number grow with large n, Mr. Pollard?
The question is, what is the relationship between little n and big N? And the answer is that little n is logarithmic in big N. Oh, this is big N and this is little n. Okay? And that's the critical choice of little n in terms of big N, for which this is less than 1. It's not always less than 1. But if the relationship between big N and little n is such that this number is less than 1, then you know that there is a coloring of big N vertices with no monochromatic little n sets. Okay. Okay, so with my last subject, I'll be very brief, and it's perhaps, I don't know, number theory is probably the oldest sub-discipline of mathematics, and like many other things, it was initially intended to be completely, people studied it out of curiosity and beauty and so on, but it became a very useful thing in recent years, mostly in cryptography. Because when you're sending messages to your bank and so on, you rely on the fact that your messages are encrypted. And modern cryptography is based very much on the availability of large prime numbers. So prime numbers, what are they? They're, they're like the periodic table that, as you know, water is made of 2 hydrogen, and 1 oxygen, and so on, and salt. This is salt. These are somehow the building blocks. And in the same way, every integer, so a prime number is a number that's divisible only by itself and 1. And the availability of prime numbers is something that is very crucial for modern technology. How do we find large prime numbers? I give you a number with 200 digits, and I ask you, is this a prime? Is it divisible by something? Well, if it happens to be even, the last digit is 6, then you know the answer is yes. But if it's not, how would you tell? So people like Henry know, Henry, what's 493? Factor it, no? 17 times 29. I thought you do this in your sleep. Some of us do. I mean, my family suffers because each time we go, in Israel, the cars have number plates which are only numbers, and I always factor them and multiply them. And I always tell Michal, go, we must tell him this is such a great number. But these funny obsessions that mathematicians have. One of them. There is worse, I hear. Okay, so we really want to find out, big prime numbers. It's really important and how do we go about this? So there is a theorem by Fermat which says this: if n is a prime number, then for every integer a between 1 and n minus 1, if you look at a to the n minus 1 minus 1, this number is divisible by n. Let's do a small experiment. Is 7 a prime? Only non-mathematicians are allowed to answer. 7 is a prime, it's not divisible by anything. Let's take n equals 7 and a equals 2. So 2 to the 6 minus 1, 2 to the 6 is 64, minus 1 is 63. You remember it's 7 times 9. Great, math works. So this has been known for several hundred years. And when the time came, when the modern need for primes came, then came the beautiful idea that why don't we turn this theorem on its head? How do we turn this on its head? Now, here we're assuming that n is prime. Now we are thinking of a situation where n is given to us and we have to decide. So we state the contrapositive of this statement. If there is an integer a between 1 and n minus 1, for which n does not divide a to the n minus 1 minus 1, then our conclusion is that n is not a prime. And we call such an a witness. A is a witness to the fact that n is not, to the non-primality of n. So at least this would be, if we knew how to use this would be a good way of ruling out somebody comes along with an n and says, let's use it for communication, for cryptography. It's a prime. If I'm able to find such an a, I can set that person away and say, no, the number that you brought me is not a prime, because I have a witness to the fact that it's not a prime. The question is, how do we find such a's? So previously, our problem was, how do we tell that a big number is prime or not? Now, our problem has become, how do we find witnesses? And so I'm lying here a little bit, and that's another thing. I often, when I teach classes, I tell to, I don't have close to zero experiment with courts, but at least in movies you say, right, they have to swear that you'll tell the truth, the whole truth, and nothing but the truth. But when I teach, I tell them that I only promise to tell them the truth and nothing but the truth. The whole truth is something that I often, shove under the rug. For teaching, it's a good strategy. And so this is what I'm doing at the moment. So not telling you the whole truth, using some very deep number theory, some very deep mathematics, you can show that there are lots of such. So I'm cheating here a little bit, but if n is not a prime number, then there are lots of witnesses. Well, that's encouraging. We need one, but we are told that there are lots. And what do you do? How do you use probability theory? When there are lots, you just sample them at random. You just sample them at random and you check. And then there are theorems that tell you that, this method works. This is a method that would be able to tell a non-prime from a prime. So this is really touching on a huge subject, and I think my time is up. So this is also a good place to start a completely different talk about number theory and prime numbers, which is, so that's perhaps when Michal comes to visit Jennifer, perhaps she will tell you about biology, but that's, okay, so I stop here. And it's also okay to ask questions now. If you still have them, that's still fine.
With the R and N question, can we get any mileage from trying to consider some sort of continuous relaxation? Like, how are these things?
I don't know. Of course, there are theoretic questions which deal with continuous objects, but I don't know of any. This seems like a very inherently discrete question to me. If you have any thoughts about this, I'd be glad to hear. But no, for this question, I don't know that there is anything continuous that people were able to do successfully. Please.
So what's striking me is you describe ways in which concrete actions, probability or needs, create these mathematical structures, which makes you think about all the other mathematical structures that might be out there for which we haven't figured out any concrete manifestations in.
That's true. That's part of.
Like Rubik's cube.
Rubik's cube. There is a lot of mathematics related to Rubik's cube. There is a field of mathematics called group theory, and you can find papers that explain how Rubik's cube is dealt by group theory, and then there is algorithmic group theory. There is a lot of good mathematics that started.
Game you can come up with.
Some games yes, and some games no.
You can find later applications that may make sense.
One of the beautiful things about these things, at least for me, is when you see really something that starts from a completely purely aesthetic or just curiosity thing that goes all the way through deep mathematics and eventually meets the real world. And some things are standard and you will perhaps even, perhaps you'll get to see it, perhaps not. But some parts of mathematics get applied, some don't. And, so it's hard to predict. Usually there is a saying by Hardy, the famous mathematician, that there is no permanent place in this world for ugly mathematics. And the other side of this is that if you have beautiful mathematics, my impression is that usually it will at some point find some application in the real world. So that also, right.